what we covered so far was univariate regression, meaning that we only had one x. The next topic is multivariate regression. So in multivariate regression, we have our target y as well as a number of x's. For example, x1 and x2 all the way to x sub p. So p predictors in total. But the idea is, just a generalization of what we covered so far. So what we're going to do is estimating some f hat, and this f hat is not a function of x anymore. It's a function of x1 and x2 all the way to xp. If we want to represent it with a vector, we can say f hat of vector x, where vector x is some, let's say, column vector, where the first coordinate is x1, second coordinate is x2, and the last coordinate is xp. So it's a matrix with p rows and one column, right? So we can also use the matrix notation here and represent the function as a function whose input is a vector, right? So for this function, we're going to have the same thing. So some estimated intercept plus beta 1 times x1 plus beta 2 times x2 all the way to beta p times xp. So to write it more concisely, we can say it's some intercept that we estimate plus sum of some coefficients I times xi when I starts from 1 and goes all the way to p, right? So this is multiple regression or multivariate regression. But again, for this, we can calculate RSS, we can calculate R squared, and so on. Now RSS is same as before. Over n data points, we take the difference between yi and y hat I and square them so that minuses and pluses don't cancel out with each other, and this gives us RSS. And again, we're going to have some R squared. R squared will be again TSS minus RSS over TSS. And when values of R squared is larger, it means that we have been able to capture more of the variation of y in our model. So that's pretty much the idea. So now with multiple regression, if I want to visualize it, let's say with two predictors, let's say this is x1 and this is x2 and this is y. So now we have points in a three-dimensional space. So these are our historical data. And instead of fitting a line, we're, let's say, fitting a plane. So we're fitting a plane to the data, and again, for each of these data points, there will be some image, which is like their shadow on that plane. And these will be, these differences, these residuals, are the components that we square and add together to get RSS. So this is with two predictors. When we have more than two predictors, we cannot visualize it, but it's the same idea. We're going to have a hyperplane, right? So this is a plane with two dimensions, essentially, sorry, with three dimensions. And then when we have p predictors, we're going to have a hyperplane in, let's say, p plus 1 dimensional space, where p of the dimensions are the predictors, and the last dimension is the target. So again, we're going to estimate these parameters. That's why there are hats on top of them, right? And we estimate them, again, using ordinary least squares. So again, we have some methodology that is implemented in statistical software, and using ordinary least squares, we're going to get beta 0, we're going to get some estimate of beta 1, some estimate for beta 2, some estimate for beta 3, all the way to beta p, right? We get all these estimates. The first one is needed for making predictions, that's the intercept. The other ones are effect sizes of different predictors. So now, if we have, let's say, we have TV advertising, radio advertising, and newspaper advertising. For each of them, we're going to get some beta hat I, and also we have the intercept. Other than the beta hat I, we're going to get some standard error of, let's say, beta hat I. There could be some t-statistic as well from the result of statistical software, and we're going to get some p-value for each of these estimates. So if the effect size for TV is 0.4, for radio is 0.2. Let's say for this one, the error was 0.1. For radio, the error is even smaller. For newspaper, let's say the effect size is again 0.2, but the error is 0.3. And the intercept essentially means the amount of sales we have when we spend no money on advertising. It's just some base amount of sale. So the intercept can be like 1,000. I mean, it depends on the units. There will be some error around it again. The intercept is not that relevant for us for making interpretations. And then for the p-values, maybe the p-value that we get here will be this. The p-value for this will be 10 to the minus 3. The p-value for this one could be 0.2. Let's say this one again, significant. So what happens here is that with this multiple regression model, TV is significant, meaning that TV advertising has a significant association with sales. This one is also significant, meaning that the amount of dollars we spend on radio ads has some association with our sales. So based on historical data, we see that when the radio ad increases, sale increases as well, right? That's just because of the patterns in the data. This is not causal, that's the other thing. Everything we talk about in this course will be just association or correlation or patterns. There is nothing causal unless we make experimentations. So only at the end of the course, we're going to talk about A/B tests. Those are essentially experimentations. And for A/B tests, we're just perturbing a system and then observing how that system reacts. And that's why with A/B tests, we can make causal claims. But everything else in the course is just correlation, as you may remember from your reading assignment. Also, the intercept is significant, but newspaper is not significant. Can you tell me why? From the values on the table. Why this one doesn't get a star? It's about p-value. So what's the problem with this value? It's not smaller than 5%, right? So let's say we're using the traditional level of significance, the traditional threshold of significance, which is 5%. This is not smaller than 5%, so this row doesn't get a star. What this means is that in a model where TV is measured and included, radio is measured and included, then newspaper doesn't have an impact anymore on sales. This is not necessarily saying that newspaper on itself in a univariate regression with sales is irrelevant. But maybe whatever relevance newspaper ads have on sales is kind of soaked up by TV and radio, because there could be also some association between these and some association between these. Maybe those people who buy the product when we have ads on TV, in newspaper, they also watch TV, and the reason for that purchase is like the combination of them. But for our model, as our model just adds these impacts, one of those variables is enough, because just exposure to the customers is what perhaps causing them to make a purchase. So these are just I'm just giving speculations. Whenever I say cause, it means I'm talking about speculations of the underlying mechanisms that are leading these associations. Otherwise, these are all associations. There's association, meaning correlation between these, and clearly correlation between TV and sales, because this is significant, and correlation between radio and sales in the presence of TV and newspaper. But whatever correlation newspaper might have had, which we don't know, is kind of soaked up by these ones. Because now this is a more complicated model where we don't have just two variables. So we cannot, from this table, we cannot say if newspaper is totally irrelevant or only not necessary for this model. From this table and the fact that this is not significant, we can say we don't need newspaper in a multivariate regression as long as TV and radio are there. That's it. But if we want to confirm that newspaper could be totally irrelevant, we need a univariate regression of sales and newspaper, and then checking the p-value for the effect size parameter of newspaper. All right, so sometimes people just get excited about p-values. I remember being at a conference when someone gave a talk, and then during the Q&A, someone just congratulated them on the p-values. It was very weird for me, but it happens. Because I guess in some disciplines, there's just too much unknown, and people are studying such complicated things that when they start the study, they have no idea of what could happen. So if at some point they get some p-value below the threshold, they get excited, right? Especially like in medical sciences, just everything is more complicated than physical sciences. For us, I guess like in engineering, we work on topics that, for which we already have an idea that this probably works, right? So we don't get as excited. But the case I just referred to, I exactly remember that it was on a medical application. But the thing is, there could be situations where everything is significant, but the effect sizes could be tiny. So we may have a table where the effect size, just to give you an example, the effect size is this, but the p-value is also like 10 to the minus 8. To me, there is nothing exciting here, because what we see is that our estimate is very accurate, that we see some significant association, but the association is not that strong anyways, because what it means, I mean, let's say for making some changes in our strategy or whatever, it means that whatever factor this value is associated with that we can control, maybe spending on TV, it has an impact, but the impact is so tiny that it's not really useful. So if we spend money on whatever channel of advertising this is, for let's say $1, we get $1 of advertising, sales increases by this much, right? Especially nowadays that people work on large-scale data, it's very normal that p-values become very small, because previously maybe in traditional fields and research designs, people had sample of 30 or 40 or 100, these numbers. Now people work on large data sets with thousands, millions, or billions of cases. Therefore, when they estimate something, n is so large that the standard error of some estimates become really tiny. And as the standard error was in the denominator of the confidence interval, it means that when the data is so big, you have your point estimate here, which has zero reliability, but standard error is really small, meaning that you can create some tiny range around it and call it a range estimate. And this range estimate could be not just a 95% confidence interval, but 99% confidence interval. And it will be still tiny. And because of this, the p-value of the effect size of that variable will show us statistical significance. But this is only relevant if this point estimate, which is beta in here, is actually some large number or some number that makes it relevant for that application, right? So if you're talking about advertising, I guess this is relevant because it means $1 spent on ad leads to 40 cents increase in sales. So it is something, right? So what I'm trying to say is that there are situations where p-value is small enough for us to observe statistical significance, but the effect size is so small that the statistical significance doesn't matter for us in applications. So that's like in the context of large-scale data. All right. So, but what are the interpretations of these estimated factors? Previously, we had beta hat 1, and we said beta hat 1 means 1 unit of TV ad leads to 40 cents increase in sales. But what about this more complicated model? The way that we can interpret this, for example, if this is TV, and beta hat 1 is 0.4, we can say spending 1 unit on TV leads to 40 cents increase in sales, keeping everything else unchanged. Meaning that our marketing campaign involves different media, right? Newspaper, radio, and TV. In that situation, if you don't change newspaper at all, don't change radio at all, only increase the budget for TV, that increase is associated with 0.4 unit increase in sales. But the thing is, this interpretation is correct, but it's a little bit problematic because in actual situations, you cannot keep all the other factors unchanged. For example, if this is about marketing, we can consider that the budget for marketing is limited. So if you want to increase TV spending on TV ads, maybe you have to decrease the amount spent on radio ad or newspaper ad, right? The thing is, in actual situations, we don't really have the control for changing one of these variables without changing any of the other ones because they are correlated. And what we have is just patterns in the data. So this 0.4 that we see is because we're essentially comparing two situations in the past where, let's say, two branches of our company had similar marketing campaigns, except that one of them had a bit more TV ad, right? And that's the pattern that we see in the data. So that's the interpretation. We can still make some interpretation. I guess we know whether this is positive or negative means something, usually, right? But the interpretation is not as straightforward as univariate regression. All right, so another example on this issue is, is the difference between the beta hat that we get for a variable in a multivariate regression versus beta hat of the same variable in a univariate regression. Here, for the examples I provided, I gave 0.4 in both situations, but typically the effect sizes change whether we use univariate or multivariate regression, because there's also some correlation between these. So one famous example about this is if x1 is the number of coins in my pocket, and x2 is the number of dimes and nickels in my pocket, and the outcome variable y is the total amount of money in my pocket, right? So if we fit, let's say we have historical data on what I have in my pocket in 1,000 days before, and we fit a regression, univariate regression on it, what would be the sign of beta 2, you know, the coefficient for x2, the sign will be positive because when we have more dimes and nickels, chances are I have more money, right? So in a univariate regression, beta 2, which is the slope for x2, will be positive. But what if I use all three of these and fit a multivariate regression and now look at beta hat 2? Beta hat 2 will be negative because in the presence of x1, which measures total number of coins in my pocket, when I have more coins, I have more money, so beta 1 is positive. And beta 2 actually is going to have a negative effect because, you know, keeping the number of coins fixed, the fewer of them are like low value coins, more money I will have, right? That's why, you know, interpreting these effect sizes in a multivariate regression is not straightforward. We may look at this and say, all right, positive, so newspaper has some positive impact. Or maybe look at this one that is statistically significant. We say it is positive, but maybe this turned out positive because of all the associations between the features. So if we want to kind of separate out the effect of one variable on one outcome, we need a univariate regression. Any questions? Sorry? Beta 2 what? Visualizing it. Yeah, definitely. There's actually a very good website. I will post it on Piazza, and it allows you to fit different lines and see how the fit changes and what are the values of beta, what is R squared, what is RSS, and everything. So yeah, I don't have it right now, but I will just post it on Piazza. It's interactive. It's just perfect. Yeah, then you will find the answer to your question. All right. So. All right. So another consideration for using a multivariate regression is that the ideal situation is that our predictors are not correlated with each other. So you may remember, those of you who had APS 1070, that we talked about principal component analysis. So with principal component analysis, we get a data frame that has column on TV, column on radio, on newspaper, and summarize these features as PC1, PC2, and PC3, where PC1 is orthogonal to PC2, and PC3 is orthogonal to PC1 and 2, right? So the idea of orthogonality here is that when two things are orthogonal, it means that they don't have correlation. And this would be ideal for multivariate regression. But if we want to keep the variables what they are, which means something in the real world, we cannot do this, and therefore there's association between them, and because of the association, whatever interpretation we give for the model is probably a bit complicated. We cannot be sure that this is 0.2 just because of the nature of radio and sales, because the nature of TV and radio and the nature of TV and sales might have had an impact on this number. So sometimes when you fit a multivariate regression model on a large data set with a large number of predictors, you may get an error of collinearity. So collinearity means that you have, for example, two features that are highly correlated with each other, and both of them being in the model is not a good idea. Then what you need to do is to maybe remove one of them. Another kind of practice is using variable clustering. That's something else that statisticians do. So the variables or the predictors that we have, first we run some variable clustering on it, right? And find a cluster of features that cover the information we have without introducing collinearity, and then fit a model on that cluster. Or maybe, pretty much that's the idea. You want to kind of remove features whose effects are also measured in other features. So if we have number of bedrooms and the square feet of different houses, and the y variable is price of a house, well, number of bedrooms and square feet are kind of correlated, right? So maybe, depending on the data set, we may get one of those errors of collinearity. This means that we need to go back, either remove one of those columns or run variable clustering and see that what is the ideal combination of variables that we should keep. Any questions? All right. So when we have a multiple regression model, another challenge is confirming whether there's at least one relevant predictor here. So there could be situations where we are just using some features that have nothing to do with the outcome, meaning that they are totally uncorrelated. That's actually happens in, for example, in biostatistics. Right? When we work with data on genes, typically we don't have any idea of which genes might be correlated with cancer, right? And there are so many different genes and so on. And then in those situations where there's some likelihood that the model we're fitting could be totally irrelevant, there is some F statistic. There is some F statistic that we get from the output of the regression model, and we can look at the p-value of this F statistic. If the p-value of F statistic doesn't show significance, then we should stop right there. it would be really unlikely, especially in situations when we have some idea of relevance between predictors and outcome. This should not happen at all. But sometimes we are just trying an idea, knowing that there's some likelihood that it doesn't work at all. Maybe we're just trying a combination of genes that no one has looked at with cancer or with some other outcome in biology that no one has ever looked at. In those situations, we need to be skeptical of what we're doing, and we definitely need to check the F statistic that we get from the report of regression and make sure that it's showing statistical significance. If this doesn't show statistical significance, it means that none of the predictors are relevant. That's really kind of a low bar to pass. So we want to have at least one relevant predictor and then get rid of the irrelevant ones. But sometimes we might have used a model where everything is irrelevant, and this shows that situation. All right, so now, so there's another topic, model selection for multivariate model selection for multivariate regression. So with model selection, we're going to talk about this, I guess, in 2 or 3 weeks from now. There's some concept of best subset. There's forward selection and backward selection. At this stage, you just need to know that there are different ideas. We will learn them actually later in the course. So with best subset selection, the idea is that we have P predictors, but P is a large number. And last week I told you that in situations where we have large P compared to the number of data points, our models could suffer from curse of dimensionality, right? So instead of wide and short data sets, we want tall and skinny data sets. So even if we cannot increase the number of n, the number of observations, what we want to do here is to convert this to a data frame where instead of P, we have M predictors and n is the same. But here P was larger than n, which is problematic. Here M is smaller than n, which is good, right? So with best subset selection, we say that instead of P, we want to use some M predictors. And for finding the best combination of predictors, we know that there are 2 to the P different combinations because each of the P predictors is either in the model or out. Either we use it or don't use it, right? That's why there are 2 to the P possible cases. And with best subset selection, we're trying to find the best subset of M predictors out of P by looking at all 2 to the P possible cases. This is usually computationally heavy, especially if P is, let's say, larger than 15, 20. That's why we have kind of simpler approaches, forward selection and backward selection. With forward selection, what we do is we start with all the possible P univariate. We start with P univariate models. So we have P predictors. For each of those predictors, we can fit a univariate regression, right? With that X and Y, right? And then within these P univariate models, we pick the best one. So we pick the one that, for example, has the highest R squared. So we pick one of them that maximizes R squared, and as it is called forward selection, we move forward. When we move forward, essentially, then there will be P minus 1 remaining predictors because we picked one of them here. There will be P minus 1 remaining. Therefore, we create P minus 1, let's say, bivariate, meaning 2 predictors, bivariate regressions. Right? What are these P minus 1? All of them have the feature that we selected here, and then they have the first remaining feature, the second remaining feature, all the way to last remaining feature, right? And then again we pick the second feature now based on which one of these P minus 1 models have the maximum R squared. And as it is forward selection, we move forward. And we just continue this until there's no remaining predictors. Or we continue this until the R squared of a model with a number of predictors matches a certain threshold. So we want to pick as many so that R squared becomes 0.7. If it becomes 0.7, we stop. Or we want to move forward until we reach M. That can be another stopping criteria. But that was just an overview. We will actually talk about it later in the course. And then another method is backward selection. With backward selection, first we fit one model with all P predictors, right? And then we look at the table of that model. It's something like this. Let's say all the predictors are just 3. We look at the model, we see this is the feature that is not significant. So let's get rid of newspaper. We get rid of newspaper. So we remove, and we move backward, meaning that when we remove it, it will become one model with P minus 1 predictors, right? And then we fit again, right? It will be one model with p minus 1 predictors. And then in this model, again, we check which variable is not significant or has the largest p-value, and we remove it. Again, so we remove, for example, for removal, p-value can be p-value can be a criterion, right? And we just continue this. At some point, this p number of variables we have decreases so much that we reach m, for example. The stopping criterion can be, there are different options, yeah?
So for the vector selection, I'm just wondering if we're doing like univariate regression with all the predictors.
No, there's no univariate. This is one, always, yeah. Multivariate is also called multiple. One multiple regression, yeah. There is no univariate in this. Again, this one is multiple regression, yeah. So this is called, that's how we find the important variables, right? So the ideal situation is this, but this is computationally challenging. That's why we have these alternatives. Also, this last, the backward selection, this one is also computationally challenging because first we need to fit one model with many predictors. That's why the best, the most common approach is actually forward selection. But later in the course, we're going to see situations where, for example, we use regularized fitting, like ridge regression or lasso regression, and they take care of feature selection for us automatically. So these ideas are actually, maybe from more than half a century ago. These are pretty old. Then ridge regression, if I'm not wrong, is from like maybe 80s. Lasso regression maybe from 90s, and those are also pretty old, I guess 30 years, right? And then topics like, support vector machines, they are maybe from less than 20 years ago. So also in the course, we're starting with some really foundational ideas that are really old, and we get more and more contemporary. All right, so these three alternatives are not all the possibilities, but there will be other methods that we will learn in chapter 6 of the textbook. For example, mallow CP, AIC, BIC, adjusted R-squared, and cross-validation. There are some methods that are here. All right, so maybe we can now take another 10-minute break, and then we can talk about qualitative features. So all these features that we discussed, they were quantitative, but there are also situations where we have discrete variables, right? Maybe ethnicity, maybe marital status, and how we can use those in a regression model.